Okay. Yeah, so the plan for today is to just either give a brief, to give a brief overview of homotopy groups. This will be review for some people, it'll be new for other people. Yeah, feel free to interrupt me or ask questions. Yeah, okay. So we're gonna define homotopy groups, talk about loop spaces, talk about why homotopy groups are abelian, state the Horevich theorem about the relationship between homology groups and homotopy groups, and state Whitehead's theorem about that homotopy groups detect if maps between CW complexes are homotopy equivalences. Okay. Yeah, so the goal for the next 2 weeks, or maybe slightly less, is to prove that the homotopy groups of the free abelian group on a space modulo the free abelian group on a subspace is just relative homology. And the goal for today is to just understand homotopy groups better. And the goal for Thursday's class is to to do the same thing except with vibrations and fiber bundles and covering spaces. And everything I talk about today will be in chapter 4 of Hatcher. Oh yeah, someone asked me last time for a document that had like a list of references, and I made a Word document and put it on the website in the Google Drive link. So yeah, people can. Or right now it just has 2 things, but I'll add more references when they become relevant. Yeah. Also, if anyone else finds any documents that they think are vaguely related to the subject matter of the course, email me and I'm happy to put it in. Okay. So we defined homotopy groups to just be the set of based maps from a sphere into a base space. And for today, it'll be more convenient to instead think of homotopy groups as the set of maps from an interval to the ith power, so like a cube, rel the boundary of a cube, into the base space. So the cube goes into the space, and the boundary of the cube is mapped to a point. And then this is modulo homotopy of pairs. So in particular, in the homotopy, the boundary needs to always map to the base point. Yeah, and so these mapping spaces, I think, are homeomorphic. So in particular, this is an equivalent way of defining homotopy groups. In the fundamental group case, it's like thinking of it as a map from a circle rel 1 point versus a map from an interval that sends both ends of the interval to the base point. Okay, any questions before we move on? Okay, so homotopy groups are groups once I is bigger than 0, and there's a formula. The formula is analogous to the formula for making the fundamental group into a group. You just pick one of the coordinate directions. So here we're just going to pick the first coordinate, and so for f and g are maps from square rel the boundary of the square. We just shrink f and shrink g and then put them into a square. Yeah, so when I is 1, this is the usual formula. And then for higher I, we do the usual thing from fundamental group in the first coordinate, and then the higher coordinates just go along for the ride. Yeah, so this gives a map on mapping spaces, and then it respects homotopy enough to descend to a map from, the ith homotopy group, squared, like Cartesian product with itself, to the ith homotopy group. And this is going to induce the group structure. And so what's the unit? So if we let x naught denote the constant map to the base point, which we're also called x naught, then the multiplication with x naught isn't literally the identity on the space of maps. So over here is a picture of f multiplied by x naught. You get f at double speed, and then on half of the cube, and then on the other half of the cube you get the base point. But that's homotopic to just f, because you can sort of shove this line to the right. Any questions? This is completely analogous to the fundamental group case. So this provides a unit after taking homotopy. So the mapping space is not a group. It's not even a monoid, because this isn't a strict unit, and multiplication isn't strictly associative. But after taking homotopy groups, it is a strict monoid. That's back to group. And so what's the inverse? Oh, there's a typo. Right. So you flip the x1 coordinate, leave the other coordinates the same. That's the formula for the inverse. So epsilon is this map on mapping spaces, and what does it do? It just sends a function. The function accepting flipped values on the first coordinate. Yeah, and so modding out the homotopy gives a map, and this is the identity. So the multiplication applied to epsilon f, comma f, homotopic to the constant map, and you can check that this formula for the inverse and the unit and the multiplication all assemble to form a group. Okay. Any? Yeah. So the next comment is that you can think of modding out by homotopy as like topologizing your space of maps and just taking pi 0. Yeah. So there's a proposition from algebraic topology, or sorry, from point set topology that at least I covered when I did 571. So it says that under reasonable conditions, so if X is locally compact in Hausdorff, then then a map from X cross Z into Y is continuous if and only if the adjoint map from Z into maps from X into Y is continuous. So the adjoint map, so if F is a map from X cross Z into Y, capital F is the map whose value on Z is the map whose value on X is f of X comma Z. And the upshot is that if you topologize the so here we're topologizing mapping spaces with a compact open topology. So that's how we're gonna, generically, if I don't say that's how we're gonna topologize mapping spaces. The upshot is that modding out by homotopy is the same thing as taking pi 0 in the mapping space.
Sorry, I was still. Can you go back to the previous slide for a second? I have a question.
Sure.
So, can you, with that picture there, possibly explain? Because when we were doing the pictures with the composing them together, you just kind of put the two things together.
Yeah.
You kind of demonstrate visually how putting those two things together gives us just X0, the identity.
Yeah. So maybe I'll draw it in the fundamental group case.
Okay.
And then, and then like it will just be you sort of take this homotopy and cross it with the identity on the other coordinates. But it's easier to maybe visualize. Oops. Looks like we have. So in the fundamental group case, the composition is the map that, let's say, first does the dark blue and then does the light blue. And then we're homotopying it. So we want to homotope it just to the constant map at red, and at sort of intermediate times. We're gonna. Oops. Not skilled enough. At intermediate times, we're just, let's say at time 1/2, we'll do 1/2 of the loop, and then 1/2 of the loop back.
And then in 2 dimensions, we just do that in the x-axis and then leave the y-axis alone, basically.
Yeah.
Okay.
So I mean, it's a little bit harder to picture, like you have some embedded sphere and then you do the sphere in the reverse direction. Maybe it's not that hard. I guess, I like, you have an embedded sphere and then you're, I don't know, like considering making hand gestures, but I don't think that would help. But yeah, you just basically do the identity on the other coordinate.
Okay.
Are there any other questions? Okay. Yeah, so this slide just says that modding out by homotopy is the same thing as taking pi 0. And I think the points at topological assumptions, I think we just need to apply them basically to the cube. So, which they're satisfied for. So I don't think this corollary has any assumptions on X, but I'm not a careful person. So if someone tells me actually X is the thing that needs to be locally compact in Hausdorff, I'll believe you.
And that corollary is just as sets because there's no group structure on the right. Yes?
Yeah.
Okay.
No group structure on the right. And then, as I said, like we're going to be interested in situations where X is an abelian group. And so then all the homotopic groups, including pi 0, inherit a group structure, and it's a a generalization of a homework exercise from 571 that I assigned that shows that these two group structures agree. So yeah. So what what you can think of is you can think of this mapping space as a group up to homotopy, which then gives pi 0 a group structure, and then this is an isomorphism of groups. If you want to think about it that way. Yeah, because all of these operations were defined at the level of the mapping spaces. However, the identity is only held up to homotopy. So this thing is not a group. It's actually relatively straightforward to replace it by a space that's homotopy equivalent that is a strict monoid. I think you can replace it by something that's actually a strict group, but okay. Any questions? Oh yeah. So in the case of just I equals 1, we're just going to rename the mapping space. I guess it's called the base loop space, and it's usually denoted by omega x. Yeah. So if you think about, so we're going to view like omega as like a functor from spaces to spaces, and you can iterate that functor. And if you iterate it I times, you just get the mapping space out of the cube. And so in particular, the oh yeah, so I guess this proposition we've stated in the case that I is 0. So we've said that pi 0 of loops nx so I guess if you believe that iterating this functor I times just gives you the maps from the I cube ReL boundary, then you should believe the proposition in the I equals 0 case. X. And then wait, thought I saw an easy way of seeing this. Oh yeah. So what you want to yeah, okay. So how do you get the higher I version? Well, I of omega n x is the same thing as pi 0 of omega I of omega n x, which is the same thing as I 0 of omega I plus n x is the same thing as I plus n of x. Yeah. So in particular, maybe I'll point out one special case of this. This is saying that pi 0 of loops in x is the fundamental group. So the fundamental group is is just the set of path components of the space of based loops in a space X. Yeah. Any questions or things I should repeat? Okay. Yeah, so maybe some more remarks about adjoint maps. So, so mapping spaces and Cartesian product are adjoint. So they're the data of a map from X cross Y into Z is the same data as a map from X into the space of maps from Y to Z, and this respects the topology. So the next comment is, okay, let's say we're in base spaces. So here the star on mapping spaces indicates that all the spaces are base spaces, and we're requiring that the maps preserve base points. I'm missing one star. Yeah, so this says that basically if you use base mapping spaces instead of regular mapping spaces, then you have the same properties, except you replace Cartesian product with smash. Because as I said, like smash is the correct product in the base case. Okay, so the corollary of this, I guess, is when you plug in y. You plug in y is the circle. Y is the circle. You get you get that loops on the space of maps from X to Z is the same thing as maps, base maps from X into loops Z, and is also the same thing as maps from the suspension of X into Z. And then now the example, if you plug in, now we're gonna, so Y is S1, and now we're gonna plug in X is S2. It says that loops on the space of maps from Sn into Z is the same thing as maps from Sn into loop Z is the same thing as maps from the suspension of Sn into Z. And the suspension of Sn is just Sn plus 1, so that's the same thing as maps from Sn plus 1 into Z is the same thing as loops n plus 1 Z. Okay. I don't know what the point is. The point is, like, there's a lot of ways of writing the same thing. Any questions or like things I should repeat? Yeah, the idea is basically if you just look at what the data is in all of these situations, it's the same data. Okay, so I'm going to give like a needlessly fancy way of proving that higher homotopy groups are abelian. The point of this is to sort of lead into operads, which we're not going to talk about for a while. So these are actually these things actually assemble to form an operad, but we won't need this yet. So let C and K be the space of embeddings of I n-dimensional of K n-dimensional cubes. This should be a K. K n-dimensional cubes into an n-dimensional cube, and I want these embeddings to just be scaling in a coordinate axis direction composed with translations. So, in particular, an element of one of these spaces is completely described by a picture. Okay, so these things are going to sort of parameterize the algebraic structure of loop spaces. So what do I mean by that? I mean that there's a map that I'm calling M for multiplication that takes a element of this space of cubes and k different elements of loops nx and outputs an element of loops nx. So maybe I'll say what it is in pictures, and then we'll try to digest this formula. So what do we need to do? So we have, let's say, I guess this is the case where n is 2 and k is 3. So n is the dimension of the cube. So in the picture, the cubes are 2-dimensional, and k is 3. So we have 3 different 3 different maps from a cube into X, and these maps send the boundary of the cube to the base point. So what we do is we take sort of a scaled version of these 3 maps and plug them into each of these 3 boxes, and then send the rest of the cube to the base point. So that's what this function says. So here G is a G is a collection of cubes. So GI, I say this somewhere. Oh yeah, so I guess I said this on the previous page. So you can think of an element of the space of n cubes as it's a collection of I different embeddings. Sorry, collection of k different embeddings from a cube to a cube. So we'll let GI be the ith one. So the formula is if so this whole thing is supposed to be a map. This whole thing is supposed to be a map from a cube into X. So if we plug in V, a point in the cube, into this expression, either V lands outside these 3 little cubes, or V is in one of the 3 little cubes. So if V is not in one of these 3 little cubes, then we send it to the base point. So that's what this row says. And then if it is in one of these cubes, we use the that we can identify this little cube with a standard cube by taking the inverse of the embedding, and then we just apply the ith function f. Someone should say they're confused now, probably.
I am quite confused, yes.
Yes. Okay. So, so the idea is, so you might have said, it's probably not your objection, but we go back to this picture. You might have said like, hey, why are you stacking? Why are you putting f on the left and g on the right? Why not g on the left and f on the right? Or why don't you put f above g? Why don't you stack in that direction? Or why don't you put f in the top left corner and g in the bottom right corner? I mean, wouldn't any of those work? Why do you like f on the left and g on the right? And the answer is, I don't actually care. All of these would be perfectly valid ways of defining a group structure on pi 2 of x. So I mean, maybe your question is details and I'm talking big picture, but so what I'm saying is that like CNK is giving us, this is a space of ways of CNK is like our space of ways of multiplying k different maps from an interval, or okay, so let me say the sentence again. So loops on X, maybe just think of as maps from a n-dimensional cube into X rel boundary. And then, the question is like, what is the space of or what is like a space of ways of taking k different n-fold loops and getting one loop, or getting one n-fold loop out. Too many things are called cubes here. Okay, so maybe let's just try to be more concrete. So are you happy with that, like C and K is the space of pictures like this?
Yeah, visually that much makes sense to me, I think.
Yeah, so then what I'm saying is, like, given a picture like this and a bunch of maps from a like a cube into X, we can assemble the maps and the picture into a new map. That's the goal. And the idea is that if you're okay, so what's the new map? Well, outside of these three cubes, we're gonna send all the points to the base point. So we're trying to find a function, like, given a point in this big cube, I need to tell you where in X it goes, right? Are you happy that that's like the, okay, so maybe I'll make a statement and then I'll ask a question. So I'm claiming that what I need to do, given these three maps and this picture of a cube, I need to tell you a rule such that if you give me a point in a cube, I give you a point in X. That, like, that's what this map M says. Given a collection of cubes in a cube, and given a collection of maps from cubes into X, I need to give you a new map from a cube into X. So, given a collection of cubes and a collection of maps from cubes into X and a point in a cube, I need to give you a point in X.
Sure, I agree with that.
Okay, so yeah, and then the question is, like, either what does this giant formula mean, or what does this picture on the right mean?
Or both.
Or both, yeah. I mean, they should be the same. So, okay, the first thing is, if the point you give me is outside of these three cubes, you give me a point in the cube, and let's say it's right here. You give me this point, I'm telling you that should go to the base point. Now, let's say you gave me this point instead. Well, I want to say take F2 of that point. But I'm not quite saying that. I'm going to say we can identify this cube. We can identify this little cube with a standard cube using this map G2. So, like, this picture on the left is a picture of three embeddings of a standard cube into a standard cube. So you've given me a point in this little cube. We have a homeomorphism between this little cube and a standard cube. So what I'm saying is, like, you gave me this point, take the inverse of the identification of the little cube with the big cube, take the inverse of that, and then apply the function F2.
And then that gives us a point in X. Again.
That gives you a point in X.
Okay. What happens if, so based on our definition of C and K, in the picture, we could have, like, box 1 and box 2 overlapping, right?
I said that, like, they're embeddings of the disjoint union in. So
right, but they could embed to the same place.
So I'm saying the stronger thing. I'm not just saying it's an embedding of each of the cubes in. I'm saying it's an embedding of the disjoint union, which means that they don't overlap.
Okay.
I'm saying it's injective on the entire disjoint union. It doesn't matter. I think we're going to let the boundaries overlap, but I mean, up to homotopy, that doesn't matter. Yeah, so maybe I'm only actually requiring that there are embeddings on the interiors. But yeah, so the idea is that, okay, like what does this have to do with anything we've been talking about before? If you take T, I don't know, I call it T. If you take T to be this element in cubes N2, then the multiplication map associated to this cube is the multiplication map that gives you the group structure on homotopic groups. Yeah, so here we're embedding, we're embedding two cubes into a cube, and we're picking the embedding to just be, I guess, chop your cube in half and view the view each of the rectangles as, whatever. Yeah, so the proposition says that if you if you take this particular T, then the multiplication map gives you the mu from before. And if you take the same cubes, but you have them in the opposite order, maybe. Is there a question in chat? Does your microphone not work, or so if your microphone doesn't work, I will try to look at chat. Yeah, so maybe if we let T prime be this picture 2, 1. This is terrible. I cannot draw 2, 1. Yeah, so then the multiplication associated to T gives you the usual multiplication, and the multiplication associated to T prime gives you the group structure, but in the opposite order. Any questions on this statement?
So just to summarize and make sure I'm understanding, all we're doing here is picking a really good T so that we get the embedding that is our group composition.
Yeah.
Okay.
Yeah. And so what we're interested in, I guess I said, I'm giving a needlessly complicated proof that these homotopy groups are abelian. Like, what is a proof that the group is abelian? Well, you just need that the multiplication map and the multiply in the other order map are the same. So I'm saying the space of cubes not only gives us our multiplication, but it gives us our multiplication in the other order. Yeah, any other questions? Okay, so yeah, so now we're just going to restrict to k is 2. So if you apply like the pi 0 functor, so pi 0 takes products to direct sum. I don't know, some stupid way, whatever. Call this direct sum. I mean, I could call it product, but I should call it the same thing in both cases. So yeah, so if we have this map, and if you apply pi 0 to it, you get a map from, oh, I know, I should call it cross. I should call it cross because these things aren't groups in a natural way. Or two of the, or I guess this formula makes sense even when n is 0. And when n is 0, these things aren't groups. And I've never said how the thing on the left is a group. So I should call it cross. So in the case that things are groups, cross, the Cartesian product of sets is the same thing as direct sum of groups. But the things aren't, not all of the things are groups. So I should have corrected my typo this way. Trying to get rid of, I can't close the chat window. I'm just drawing over it. That is, okay. And annotate. Okay, so we have these two elements in C and K. Oh, another typo. This is the 2. Close chat. This is a 2. This is a cross. Yeah. So we have these 2 different elements in Cn2, and then the claim is that when n is bigger than or equal to 2, they're the same element in pi 0. So or a stronger statement, all these C and Ks are connected once n is bigger than or equal to 2. We only need this in the case that K is 2, but they are all connected once n is bigger than 2. So how do we see that it's connected? Well, or how do we see in particular that our the two configurations of cubes are in the same path component once n is 2? Well, you take these big rectangles, you shrink them down to little squares, and then you move them around each other, and then you expand them to big rectangles. So our multiplication map on homotopy groups and our multiplication map in the other order on homotopy groups both come from picking an element in Cn2, and then after taking pi 0, those are the same element once n is at least 2, so they give you the same map. Yeah, so sort of the space of all multiplications is connected once n is at least 2. So that's why, the space of multiplications contains regular multiplication and multiply in the opposite order. So those two things are the same after taking homotopy. On the other hand, when n is 1, if you're dealing with a fundamental group, it's definitely not abelian, and because there's no other direction for us to rotate the cubes around in. Yeah. I'm happy to say more what this path is, or just say more about the formalism. Okay. Great. Okay, so the next topic is the relationship between homotopy groups and homology groups well, we'll start out in low degrees, and then I'll state a theorem in higher degrees. Okay, so H0 of x is just the free abelian group on the set of path components of x. So you're trying, you have a group, and you're maybe one way of thinking about it is they're as isomorphic as they could be. Pi 0 is a set, H0 of x is an abelian group. You can't compare sets and groups, but you can take a set and turn it into a abelian group by just taking the free abelian group, and then they're isomorphic. Yeah, so this is something hopefully you've seen before. And then also, if x is connected, H1 of x is the abelianization of pi 1 of x. So, again, you can think, okay, they like really want to be the same, but pi1 of x is not necessarily a abelian group, and h1 of x is an abelian group. So we're just like taking our non-abelian group and making it abelian. So we're just modding out by all commutators. Yeah, but there's one sort of caveat. This theorem is not true when x is not connected. If x is not connected, the theorem is true for each path component. Oh yeah, whenever I say connected, I probably mean path connected. Because this is algebraic topology, so connected is not an important notion. Whatever. Cannot write. Path connected, typo. Okay. Yeah, so in general, it would be the direct sum over path components of the abelianization of pi1 of x with base point in that path component. Okay, so the generalization to higher degrees says that, so let's assume that x is path connected and simply connected. Then the statement is that if the homotopy groups vanish for all I less than d, then the homology groups also vanish for all I less than or equal to d, and the first time, and pi d of x is the same thing as h d of x. And similarly in the other direction, if the homology groups all vanish for I less than d, then pi1 of x is vanishes for I less than d, and in degree d they agree. So what this is saying is that in the first approximation, this is saying that the vanishing range is the same, and they are both, and the first time they're non-zero, the two groups are the same. We definitely need d bigger than 1 because d is 0 the first time they're non-zero. They're definitely going to be different. And oh, I guess typo, more important typo. Theorem is false unless I say reduced homology. I should say reduced homology here. And I can't open chat. Okay. Yeah. And caveat, so we do need this condition. One of the directions we don't need this condition that the fundamental group vanishes, but the other direction we definitely do. Like it's possible that you could have a space where like the first 10 homology groups vanish, but pi1 is non-zero, but it just is a group whose abelianization is non-zero. So if you want to use the homology vanishes implies homotopy vanishes, you need to sort of add this extra condition explicitly that the fundamental group vanishes, because sort of some information can be lost in abelianization. Okay, any questions? Yeah, so corollary of this tells you that that the first, the homotopy groups of spheres in degrees smaller than n are 0. You know what pi 0 of a sphere is, so if you think my statement is wrong for that, well, you know what it is, so it's fine. And it says that pi n of Sn is z. Yeah, so that part makes sense, and then you might say like, well, I don't know. Oh yeah, but I get the weird thing is it turns out that there are higher homotopy groups. So if the homology of something n-dimensional, there isn't homology. If you have an n-dimensional space, there isn't homology in degrees bigger than n. But that's definitely not true for homotopy groups. So in particular, the first example was I3 of S2 is Z. And I think there's some story that I don't really know the history, but Hoff proved this and then also observed that all the higher homotopy groups were abelian. And then people said okay, then clearly you have the wrong definition of homotopy groups, because we want non-abelian groups and we want them to vanish above the dimension. And then he retracted his paper. There was enough criticism. Yeah, I don't know. Some version of that is true. Yeah, but then eventually, people decided that this was the correct thing to call higher homotopy groups. Okay, so just in case you're wondering, I think I stole this from Wikipedia. Maybe I'm supposed to credit whoever made this table. Here's a table of homotopy groups. So the higher homotopy groups of S1 all vanish, but once you get to S2, yeah. So I guess one thing to say is, okay, the in degree n we have z's, below degree n we have zeros, but then we have crazy things. I guess we have the z that Hoff discovered, then there's some z mod 2s, and I don't know, z mod 84 somewhere. Yeah, but there is, the only obvious pattern other than we got zeros for I less than n is that if you go out on a diagonal of slope 1, it's eventually constant. So here it's always z. Here it's eventually z mod 2. In the beginning it's 0 and then 0 and then z, and then it becomes z mod 2. The next diagonal is zeros and then it becomes z mod 2. Got some z mod 2s, or zeros, then z mod 2, then z mod 12, then z cross z mod 12, but then it becomes z mod 24 and stays that way. Yeah, so these homotopy groups stabilize, and most of the effort is in calculating the stable values. Those turn out to be slightly more interesting and slightly easier to compute, but I think all homotopy groups are interesting and hard to compute. Okay.
How does one even go about approaching computing some of these higher ones?
Yeah, I mean, so next class we'll give given a bunch of things that I won't prove, but are not that hard, I'll tell you how to compute pi 3 of S2. And then maybe I'll try to sort of hint at how you would try to calculate higher ones. I mean, it's definitely right now sort of by hand. We've not figured out how to make computers compute any of these things. The first approximation, okay, so here's a vague statement, but you want to try to approximate homotopy groups as automorphism groups of homology. Is a right thing. It's not the right thing to say. Oh, okay, maybe. Okay, here. Okay, so the here's the method. Here's a method that basically Sayre invented and got him a Fields Medal. Maybe his was slightly more sophisticated, but basically what you want to do is you want to, how did we compute the first one? Well, like we use the Hurevich theorem. So like homology is easy to compute. Homotopic groups are hard to compute, but sometimes they're equal to each other. So what you want to do is you want to, initially we applied this theorem when, for x is Sn. What you're going to want to do is you're going to, so there's like, what is the universal cover? Well, the universal cover is a space whose, one way of thinking about it is it's like your space, but you've made the fundamental group trivial. There are higher covers where you make like the fundamental group and pi2 trivial, or you make the fundamental group and pi2 and pi3 trivial, but you keep all the higher homotopy groups the same. So then you just need to compute the homology of these spaces, but they're kind of crazy. So what you'd want to do is you'd want to, so like what we're going to do next time is we're going to say that S3 is like the like a higher analog of the universal cover of S2. So it's going to, and in particular, it's going to have the same homotopy groups starting at pi3. But now it's one more connected. So like it'll be like pi3 of S2 is going to be the same as pi3 of S3, but then we're going to be able to compute that because that's equal to homology. And then now we just need to find a space that's one more connected than S3 and has the same same higher homotopy groups. And then we just compute the homology of that space. But they stop being geometric. Like it's sort of a low degree accident that this generalized universal cover of S2 has a geometric description of just S3. In general, they're not spaces that you draw pictures of. I mean, not that you really draw a picture of S3, but they don't have like geometric descriptions, and they're going to have infinitely many cells. But you can still sort of attempt to compute their homology. And that's like the zeroth, or that's like the first order approximation of how to do this. And that maybe gets you like that gets you, I don't know, like 2 to 8 degrees above the line where they're all z's. And then you just sort of think about what you're doing and try to do it all in one step instead of iterated steps. And there's something called the atom spectral sequence. I don't actually know how to compute. If you asked me to rigorously prove that like pi6 of S2 is Z mod 12, like I feel like I could read a proof in under 3 hours, maybe. But like I could not on the fly tell you how to compute that. Or given 3 hours and not the internet, I would not be able to tell you how to do that. I don't know. Hopefully that answers your question.
Yeah, I didn't figure the answer would be easy, so I was just looking for a high level.
Yeah. I mean, so you end up sort of you end up sort of building these like designer spaces that have good properties from the like perspective of homotopy theory, but don't arise like sort of geometrically. And I don't know. And that's, I don't know, a thing that happens. Okay, so what were we talking about? Oh yeah, so like what actually induces this isomorphism? So I said like if the homotopy groups all vanish in some range, then homology is isomorphic to a homotopy group. So I should tell you a map. I'm going to tell you a map, and then I'm going to draw a terrible picture, like, or give you a cartoon sketch of the proof of the Hurevich theorem. Okay, so but the map we should be able to define rigorously. So this thing brackets SI is going to be a preferred choice of generator of the reduced homology of SI in degree I, which is just Z. I guess I'm saying reduced homology so that way the statement works when I is 0. Not that we really care about I equals 0. So this brackets notation is like for the fundamental class. So if you know about Poincare duality, it's the same, but just, top homology of a sphere is Z, and I'm just saying pick a generator. There are 2 choices of generators because there are 2 choices of, Z has 2 generators as an abelian group, 1 and -1. And, this isomorphism isn't canonical, so we don't know which one is 1. So just pick a generator. So the Hurevich map, I need to give you given an element in homotopy, I need to give you an element. I need to tell you how to get an element of homology. So, I guess this brackets means class of. This means homotopy class of, whereas the other one doesn't. So, I have a map from an I sphere into X, and so that's what an element of the homotopy group is, a homotopy class of maps from an I sphere into X. How do I get a homology class? Well, I just look at the induced map on homology and plug in the generator of homology of maybe. Annotate. Yeah, so maybe I'll just say, so F star is a map from from homology of SI to the homology of X, and just plug in your favorite generator of the ith homology of SI, and then apply the induced map on homology. That gives you a homology class in X. Okay. Any questions on how this map is defined? So if you want to sort of think intuitively, so not every class in the homology of X comes from a sphere, and the Hurevich map is sort of asking, which ones come from spheres. So you should sort of think of homology as the space of, like, you think of the ith homology group as the space of I-dimensional things without boundary modulo boundary of I+1 dimensional things. But things need not be spheres. And the Hurevich mapping and isomorphism is, it says that your I-dimensional things are equivalent, where equivalent means like co-bounds, is equivalent to maps from spheres. So my cartoon sketch of so what you should your canonical picture of something that's not in the image of Hurevich is going to be like H2 of a torus. This is not a proof, but if you just sort of think about it, how are you going to map a sphere in to a torus that sends, like, that wraps the sphere all the way around the torus? Like, how are you going to hit the generator of the torus, the top homology of a torus, with a sphere? Maybe it's. I wish I could have said something better for the last sentence. And part of that is, like, a torus has homology in degree 1, and that sort of allows you to have homology in degree 2 that doesn't come from spheres. Okay, so on the other hand, let's imagine X. Okay, let's see what I wrote. This is not. The Hurewicz theorem isn't super hard, but I'm not. I'm not trying to give like a full course in algebraic topology. I'm trying to just sort of give enough for us to understand the stuff about configuration spaces. Okay, so so what's the idea? So we're going to suppose that the homotopy groups of some space vanish in degree less than n, and we're going to take this homology class in degree n, and one of the things the Hurewicz theorem tells us is that this is in the image of pi n. So let's try to sort of think about why that might be true. The Hurewicz theorem is stronger than this, but this might give you a flavor of why it's true. So you can think of what is F? F is a sum of maps from simplices in. Well, you can sort of assemble those things together like they don't have boundary, so you can sort of view F as a map from an n-dimensional simplicial complex into X. The simplicial, I'm going to call the simplicial complex Z. And the problem is that Z, Z might not be a sphere. If Z is a sphere, then we're done. Then this homology class F is in the image of the Hurewicz map. So I'm going to let like ZK denote the K skeleton of Z. And then the observation is going to be that because all the homotopy groups below n vanish, that F restricted to the n-1 skeleton of Z is null homotopic. So in this picture, X is like a two-sphere. We have a map. Z might like glue together to form a torus. We map from a torus into a two-sphere, and then this two-sphere is a simplicial complex. It's it's a bunch of triangles glued together. And then I'm saying that if you look at the one skeleton, so the edges of the triangles, that's some map from a graph into a two-sphere, so it'll be null homotopic. Because we're here, I guess, in the picture, n is 2, so we're assuming that pi 1 is 0. So any map from a graph n will be null homotopic. So what we can do is we can sort of collapse the red to a point intuitively, and then that will replace Z with a wedge of spheres, one for each top cell. So if you take a simplicial complex and you mod out by, if you take an n-dimensional simplicial complex and mod out by its n-1 skeleton, you get a wedge of spheres, one for each top cell. And then like these, then you look at like F on these spheres and like add them to get up, add it all up, and then each of these, this is supposed to show that it's in the image of Hurewicz because it's equivalent to a map from a wedge of spheres, and then you just add up the maps from the individual spheres in pi n. Yeah, and so equivalent is in scare quotes. Yeah, so okay, so this is not a real proof, but I'm happy to attempt to explain what I mean. Yeah, okay, I'm going to say one sentence, and then maybe we'll move on. Like what's a class that might not be in the image of Hurewicz? Well, if you can map a torus into a space, then you can look at like where does the top homology of the torus go in I2 of X, or sorry, in H2 of X. Like, there's no reason for that homology class to be in the image of like a map from a sphere into X. But if X is simply connected, you can collapse the one skeleton, then the one skeleton of the torus maps to, some loops in X, which you can all collapse down to a point, and you can use that to say that your map from a torus in homology is really equivalent to a map from a wedge of spheres. And then that's how you sort of show that it's in the image of the map from homotopy to homology. Okay, I'll pause for 15 seconds to see if someone asks a question, but it's this is not a rigorous proof. Oh, okay, we have. Let me quickly state. I'm going to quickly state Whitehead's theorem, and then I'll maybe let people leave and then talk for another 8 minutes. But people should definitely feel free to leave. Okay, so Whitehead's theorem says that if you have a CW complexes X and Y, then you can tell if a map is a homotopy equivalence by checking if the map is an isomorphism in homotopic groups. So a map between CW complexes will induce an isomorphism. Sorry, a map from between CW complexes will be a homotopy equivalence if and only if it's an isomorphism on homotopy groups. So it does not mean that two spaces are homotopy equivalent if and only if they have the same homotopy groups. That's a stronger statement, and that's false. But it does say that if you can find a map that is an isomorphism on homotopy groups, then the map is a homotopy equivalence. If the spaces are nice. So I don't know, if anyone has remembers point set topology, but there's a space called the topologist sine curve, and this is by far the best picture I've drawn in this class. So it's a space, and it's connected, but it has two path components. Two path components are like the y-axis and then the squiggly part. So there's a map from S0 into this space that induces an isomorphism on all homotopy groups. Because S0 has two path components, so does the topologist sine curve, but it's not a homotopy equivalence, and that's somehow that this difference between connectedness and path connectedness is not something that algebraic topology sees, or that homotopy theory sees. Okay, so this is people can leave now or ask questions, and then I'm going to, if anyone stays, I have 5-minute discussion about what the pi n+1 of Sn looks like, and why it becomes Z mod 2 instead of Z stably. Okay, yeah, any questions? Okay, yeah, people should feel free to leave, but now I'm gonna, anyone's interested, I'm gonna quickly say what the pi n+1 of Sn is, and why you shouldn't be that surprised that it goes from being Z mod, it goes from being 0 to Z to Z mod 2. That's, it's not a proof, but it's, I'm gonna at least tell you what the generator is. Okay, so the first observation is that pi n+1 of Sn is just pi 1 of the n-fold loop space. So you might be like, hey, I can't visualize, I can't visualize a map from S4 to S3. And I'm like, great, neither can I, but I can visualize pi 1 of a space, maybe. Okay, so that's the first reduction. And then you're like, well, but loops n, Sn is a more complicated space. That's the price we pay. Okay, so the next comment is that Sn acts on the space of cubes, and it acts on loops nk loops nx to the k. So the k cube space is it's k different embeddings, so it can permute the embeddings, and here it's k different maps, it can permute the maps. And so if you quotient by the diagonal action, we end up still getting a map to loops n Sn. So if we maybe go back to this picture, it doesn't matter if you it matters like which box you put Fi in, F1 into, but it doesn't matter if you called F1 F2 and rename that box 2. It matters which goes where, but it doesn't matter which one is called 1 and 2 and 3. So that's what this is saying. So that the map was Sn or Sk invariant, so it induces a map on the quotient. Next, okay, we're gonna I guess pick F to be a map of degree 1. So you're a map representing a generator of pi n Sn. And then what we're gonna do is we're gonna plug in 2 copies of F into this formula where k is 2, and so it'll give us a map from 2 n-dimensional cubes modulo Sn into loops n Sn. So in pictures, what am I saying? I'm saying given 2 cubes, we're going to plug in this preferred map F, which is a generator of pi n Sn, and so given 2 cubes and this map F, we get a map from the space of cubes into loops n Sn, and in fact it's equivariant, so we can mod out by S2. So in particular, we don't know which cube is which. Oh yeah, any questions? I think I'm talking fast. Okay, so the next claim is that if you look at the space of 2 cubes in a cube, that's homotopy equivalent to Sn minus 1. Try to draw a picture. Add a drawing the number 2. Okay, so why is, let's take n as 2. Why is this homotopy equivalent to an S1? Well, up to homotopy, you can make the cubes really small and then put the cube labeled by 2 in the middle, and then the S1 is just the cube labeled by 1 going around the cube labeled by 2. And in 3 dimensions, we'd get an S3. And then when you mod out by the way S2 acts, it flips, or maybe a better way of saying it is you can look at the vector going from the center of the 1 cube. Look at the vector going from the center of the 1 cube to the center of the 2 cube. And normalize so it's length 1. That'll give you an element of the sphere, and that's a homotopy equivalence. And now when you mod out by S2, you can't say the vector going from the 1 cube to the 2 cube because they're no longer labeled, but you could still talk about that line. And that line is a line, it gives you an element of Rpn minus 1. Okay, so then the next comment is that pi 1 of Rpn minus 1 is 0 in degree when n minus 1 is 0. It's z when n minus 1 is 1, because, remember Rp1 is S1, and it's z mod 2 otherwise. So if you assemble all these isomorphisms and maps together, we get a map from pi 1 Rpn minus 1 into, well, the space of cubes into then the fundamental group of the loop space into pi n plus 1 Sn. And then the claim is that this map is an isomorphism. And so it's exactly because like the fundamental groups of Rpn minus 1 eventually become Z mod 2. That like the stable homotopy groups eventually become Z mod 2. So, you know, at the end of the day, what is this picture? I'm saying we have this map F, and we want a loop in the loop space. So the loop is just these two functions, these two cubes F do a half twist. So the cube on the right becomes the cube on the left, and the cube on the left becomes the cube on the right. And once we're in higher dimensions, if you do a half twist twice, that's a full twist. Half twist twice is a full twist. And if we're in 3 dimensions, we can sort of bound that by we can null homotop it by going up. So that's why it stops being Z and becomes Z mod 2. But in 2 dimensions, doing a half twist twice can't be unwound. Because it's, I don't know. I don't know that I was understandable, but if anyone wants me to try to be more understandable, I'm happy to say more, or people can leave. Sorry for running over. I'm going to pause the recording.